our result. So we have 10 questions. So first discussion, we will cover 5 questions and then we open for discussion each other. So you can ask any question to anybody in this room. And first one was the strategy to make a desalination more cost effective. So as you know that seawater desalination has been two major breakthroughs so far. So 1970, we had a RO membrane, thin composite chemical membrane. It has been really high flux and high rejection. That's the make this kind of reverse osmosis seawater desalination happen. And second breakthrough was energy recovery device. So pressure exchanger, also turbine exchanger. So we try to make a more cost-effective, energy-efficient desalination. Now it's already 1990s for the second our major breakthrough. So we are in 2020. So after 3 years, so we expect another third breakthrough of the seawater desalination, and then we expect what could be the best way to make more cost effective. So people believe 80% integration of the resource recovery will be the next target. We can focus energy still energy saving device can be improved, and the pre-treatment and mitigating the membrane fouling, so salt gradient power. So resource recovery is definitely we are right direction, and then everyone believe the next third breakthrough can happen from this integration of the resource recovery. So this is what we can focus. And second question was the most promising method, salts that can be recovered from seawater out of brine. And then people believe, yeah, magnesium, lithium, sodium, rubidium, potassium, followed by others. So magnesium, lithium, sodium, even though Nikolai mentioned about bromine and some other, yeah, definitely.
Well, that is a particular niche. I mean,
Yes.
Unless you're in the oil business, it may not be that widespread, like compared to magnesium, which has multiple uses in multiple industries. I mean, it's not just an oil industry. So,
Right.
I do believe what you have is very much real. I mean, magnesium is the most valuable, actually, metal that we could extract from the bivalent metals by far. Compared to sodium chloride. The value of it, if you look at it from in a ton of water,
Yep.
is the highest at this point on the markets based on market prices.
Okay. That's what it is. Yeah, we can select this kind of prioritize to metal and the resource, and then we can make it happen for this commercialization and larger scale.
One element that's not there is calcium. And calcium is quite a lot in seawater.
Yeah.
But I think it's not there because the uses are not there. We want to carbonate and get rid of it, and that's fine. But is there a case that there's no market for it because nobody could get, or is there a market can be developed around calcium metal? And
Calcium metal, you mean, versus sulfate. I mean, obviously gypsum and others are.
Calcium chloride is worthless.
Yeah, they are. Yeah, they're so abandoned. Yeah, they're so abandoned that there's no way we could compete. Yeah.
So I say, think forwards, don't think back. We talked with Knuth. Knuth are the world's biggest producer of gypsum, and they are now panicking.
That they're running out of it.
They're going to run out of all that fluidized gas desulfurization because all the coal plants have been turned down, and that's where they produce all of their gypsum from. So the price of gypsum, if you start to look, is starting to
May start look interesting. Yeah.
But it cannot be shipped far away. That's what we have been told.
So all it is, what does gypsum turn into is majority is plasterboard. So it turns into plasterboard and then you can ship it. Then it has value.
Mm-hmm.
So in Australia, we have a large amount of gypsum utilization for the mostly like the rural area. They need a road, and the gypsum is good to have no dusty and then this kind of material. But I'm not sure in your application what kind of gypsum.
It's construction materials of various shapes. I mean, plaster walls are the most common because that's municipal construction. So you have a lot of demand for it, especially this. The preset designs. But I mean, your question is and that's a good way to look at it. What's in the future? What industries are out there that are lurking at the background that will suddenly become, a major source or major demand for some of those metals. So calcium at one point may become very valuable.
It's a whole conundrum. If you make it, somebody will take it, or you need somebody to take it before you make it.
Yeah, I mean, it's difficult to sustain this financially unless you have the demand for it. So that's why I think the way we looked at sodium chloride, and we used technologies that exist, is not that we don't know there are other technologies may be more efficient in doing certain components of the process. But if you want to commercialize it, the problem you face is you have to have commercial components in your system. Although you may have a great system for bipolar ionization or technologies that are very applicable to small niches, where you extract minerals. When you're looking at this big scale, you got to really, everything is driven by price to me. Price defines and purity. I mean, price ultimately defines purity. Purity defines everything else. So you kind of have to go backwards from those perspectives. Yeah. But creating new markets is interesting because as you have all those things like side products, like we have this huge bivalent stream from the plant that I mentioned, which we're dumping to the ocean. It has tremendous amount of value in it.
Yeah.
Yes,
We're just not exploiting it yet because we haven't, built the comfort of commercializing it. It will happen.
So the thing is, what I don't see here is big data machine learning.
Okay. In fact, that's the exact comment for the future. People are mentioning about IoT and
so big data.
Yes,
I think
right.
at least for big operations is the way to go.
Yeah.
Mm-hmm.
So, for example, what Sinafta now is doing, in this, I don't know what they're doing now, that they're bought off by Gradients, but Acciona, I remember a couple of years ago in the presentation that they had machine learning from.
Yeah, I'm actually involved in their project.
I believe.
It is, yeah, they use it in Alcover, but the system was created first. They do have machine learning system they implemented in their power business, Acciona, in a facility in Pamplona, which is, that system has operated for a long time. And now they repeated the same principles for desalination. They've been building it since 5 years ago, and now it's fully operational. The way it goes with the systems, what they do is, and it's really interesting, they are tapped into their existing desalination plants remotely. So there's a remote center as big as this, actually bigger room, where you could see on one big panel all the desalination plants. At any plant you have flow, production, power, and cost, lifetime. They know exactly how much they produce, where, and how much energy it uses. I'll probably take some of you guys to see it because it's amazing. And they don't absolutely share any information of it because of the importance and the value of it in the future. Yeah. I think that is one area that I would say would revolutionize everything, because when they started the system 3 to 4 years ago, the way the system works is very interesting, and I think that will be the future in operations. The system remembers how operators from various plants they have and they run acted on various problems. And what it creates is a database that shows up as two screens in front of you. The first screen actually shows when there is a problem, it tells you what is potentially the cause of the problem. So you see 5 dots of and a number next to them. That's the probability of this being the problem. And it gives you the five most likely problems. And it tells you what they are. And that's based on learning from other projects, same problem. Now, the operator is expected to click one of them based on his own assessment, which is the one of the 5 in his case. And then once you click on that particular button, you would get 5 potential solutions, which are also based on past experience remembered from all the other desal plants of Acciona. What is interesting, year 1, when they showed me the system that was about just before the 2019, the system was able to make a rightful decision of what to do and to solve the problem about 10% of the time. Now that is there in year 3, or 4 now, they're basically at the point where 75% of the time the machine actually makes the decision and it's correct. So when you think about, so the machines basically took 3.5 years to learn and be 10% accurate to now 75% accurate in action. Because what happens is if the operator doesn't react in 10 to 15 minutes on pressing the button of what are the causes, machine takes over makes the decision and takes over and makes the decision of what to do. Now 75% of the time that machine is correct. So imagine only in 3 years the machine, and that is because they're tapped into about 250 desal plants they operate worldwide, and they'll remember every single problem and every single action. It goes into a central computer which learns everybody's activities. That is a huge way to expedite learning and experience. And then the guys in the central control room, as I said, have a huge panel, and they are the ones that actually solve the rest of the problems, because still there is about 25% that machine cannot solve. And the way they solve it is with, they wanted to ultimately end up with unmanned operations. Their goal is to become a milk factory, as they were telling me. Because you go to a milk factory, you're not going, factory that makes pasteurized milk, you would not see a single person. It will be fully automated day and night, and it's a high, it's a food product, like water, high reliability process. So what they wanted to do is ultimately, by this type of machine learning process, is to have the centralized control take over and solve the problems. In the power generation sector, they have the same, the one that I said on this side is in Madrid, the other one is in Pamplona. In the power sector, they're now 90% accurate. And 10%, they don't even maintain, they don't have O&M teams anymore on the plants, the power plants. They actually have centralized teams, and they send them, and they have this videos, and I've seen it how, a problem was solved for one electrical case. They send the guy turns on, he says, okay, look at this, and say, check this, check that. The guy in the central control room tells the other guy in Chile what to do, who is having that screen thing. So within 10 minutes they figured it out and they fixed it. So you still have man interaction, but it's amazing that with a high level of automation you could get to 80-85% machine taking care of it without you.
Right.
Anybody being.
That's true.
So that's where the future is. So I absolutely agree that machine learning will be extremely valuable, and in the future will become.
Even in small operations, if it is handled like.
Well, the other thing is, once you have this database developed machine learning process, or database, or big data as you call it, then you could basically sell that. It's an intellectual value in a box. You could sell it, and okay, you're a new operator. Well, okay, I can sell you this product, and now you could do what I
it's
can
basically
do.
like a cheat sheet to Nikolai's book for maintenance.
No, my book doesn't actually talk about it, but the reality is this is now happening, and Acciona is on the forefront of it. They actually combined their efforts with Siemens, so Siemens created a lot of that activities. So I think that's one thing, and then the other thing I would say, if you, besides the machine learning, is actually material, because currently we suffer, one of the main things we suffer from is corrosion, and having to deal with super duplex stainless steel, which corrodes doesn't matter. Conditions in these plants are tough. So, and I'm surprised that they didn't show it, but Asahi, which is a Japanese company for plastic, they were planning actually on this conference to announce a full set of high pressure plastic piping.
Okay.
And their vision for the future, which I believe will happen. So basically, all steel will be replaced by plastic in the future. That will revolutionize the industry, because corrosion will disappear suddenly, and that means reliability will go up, and human interaction and intervention and expense will go away. They were planning actually to introduce that product this year at this conference, but I didn't. I don't know why. But it exists now from a very reputable plastic manufacturer. It's a high density polyethylene type of material. That's the chemical base. I do believe that this and carbon composites will completely revolutionize the industry. Because and where everything is going is towards turning everything plastic. Now the vision of Asahi is, when you build this desal plant, there's nothing but 2 big bags of chips. High pressure chips, plastic chips, low pressure plastic chips, and a 3D printing machine. And you could print any component, most components, not any component, because you still have motors and things that are not, will be electrical. But basically most things will be plastic. So I think revolution in material science for components would be the next big thing that is coming, and that will make major change, because you no longer have to ship pieces of equipment. You could print your pump or pump components on site, and all you do is you get the software from the suppliers. They've been doing that actually. There is a water plaza in Japan where it is funded by the government. They don't say anything. I mean, nowadays nothing important gets published anymore, but this is one thing that's happening, and Asahi is leading it. They've already developed a series of pumps high pressure and low. They even have high pressure plastic pumps now. That would ultimately, the goal of it is to those to be 3D printed, and they do have the 3D printers for some of them already. So you basically get a bag of chips. And the other beautiful thing is, let's say you have a piece of impeller that already is, worn off, and you have to replace it 3 years or 5 years from now. You do have a grinder, and it turns into chips, which then can be recycled and print your next pump. So you're getting to this what we call circular economy at about 70 to 85% of the products will be recyclable, because all it's plastic, all can be turned into chips and reused for printing. So no longer shipment of big equipment, pumps, carbon footprints of all that. That's where the future is, and that can only happen by revolutionizing the material science and material industry, and it's happening. The Japanese are doing it; they're just very quiet about it.
All right, thank you, Nikolai. And the next question: Q3 is the technology most suitable to be applied for recovery resource from Brine. So we got a highest number of our score, the membrane technology, nanofiltration, reverse osmosis. So that's still very important. Also electrochemical process we discussed in the morning. Also selective ionic change material, morph and curve, or also crystallizer, chemical precipitation. So people, we need to selectively develop some of the membrane technology. Nanofiltration is becoming more important. So that's our Q3, and then Q4 pathway to
My
tackle.
very quick comment would be,
Yes, please.
from a neon perspective, you've got to consider everything.
Yeah.
You can't focus on looking for individual solutions when the most feasible and economical way of doing something is by chemical precipitation.
Yeah.
So you can't just ignore it.
Absolutely. They are combined together. It's not only one single process. It has to be a lot of pre-treatment, a lot of post-treatment, a lot of
Chemistry still has a lot of
membranes,
role to play in our processes, not only
Right,
membranes.
that's true.
Yeah.
That's exactly what we need to discuss. Also, Q4 is pathway. Yeah.
Just a comment on this
Go.
this chart that you've got here, if that's the point we're discussing. Public perception is important to the adoption of desalination, particularly in skeptical markets such as California. Not in
Thanks
other
God that the
markets
rest of the
that
world
have
is
their-
different.
When they look forward, aren't
We just
facing
do as we're told.
backward. But also the regulations are extremely important in markets like California and also Australia.
Yeah.
That said, the bottom line is always cost. My 2 cents.
That's what drives everything.
Right. That's true. That's true.
Yeah, I mean, one thing that I hope the Trump government comes back to power for one reason, just about a year, and it's because of what you said. That's why I mentioned it. Just about a year before the changes, I was approached by the Trump cabinet, the EPA guys, and they said, why the hell do we have 2 different acts regulating water, Safe Drinking Water Act and Clear Water Act, and why don't we have just one Water Act, because it's the same water, and we look at from a legal perspective, the gentleman I was talking to is a legal expert, and we look at the same substances being regulated in 2 different ways and at 2 different levels, and it doesn't make logical sense to us. So why don't we just simplify? And they asked me to actually join a committee, the President's committee, on that, to develop one Water Act, eliminate Safe Drinking Water Act, and 2 different acts that regulate now drinking water and wastewater, which we have in the U.S. and many countries as well. I mean, it's similar in Australia, similar in many other Singapore, other countries, and that will make a major change, as Dr. Langhart was saying. Regulations, and when you start looking at water as water, just forget about wastewater, seawater. Just consider it water with various impurities in it. That would dramatically change everything, because there are many of those types of discrepancies between the same substance, looked at in wastewater in absurd levels versus in drinking water in much higher levels, so acceptable. So the lawyers look at it and say, we can't make it, from a logical perspective, we don't see the reasoning. And there's always history behind how those parameters and levels were arrived at the point they are. But they just wanted to revamp that and say, we just want to simplify, and because it's one water, we want to have one more act replacing the 2 other acts. So I think these kinds of revolutionary changes in regulations hopefully will start making people, will allow people to start looking at water differently than we do today. So That's why I'm giving a credit to those guys, because I've never heard anything like this with the new government, which has created more problems than solutions as far as I'm concerned.
If we have immigration to Australia, I'll be coming if Trump is reelected.
Okay, fair enough. Yeah, but yeah, that regulatory framework is really killing us as an industry, I think.
So last question from this discussion timing. So does the current country that you are based in rely on desalination technology to generate fresh water? Yes, most of them, yeah, they have a more than 50% for this survey. So they are very much relevant to our also desalination and resource recovery. So that's the first session, and then the rest of the Q&A, and then all the data will be presented by the Gayatri. So now so we have another 5 to 10 minutes, so we can have any question open to, maybe if you have any some burning question to specific person, so you can just, we have a 10 minutes share, and then we can go for the second session. Any question from Anthony?
Just for the group, is it worthwhile, or is the level so low that it's not economically of interest to look at uranium and gold in seawater recovery as well? Because they are high value components, but are they not there in enough levels?
Yeah.
Yeah.
Yeah, I agree. I mean, the way we kind of introduced it, yeah, go ahead.
Sorry, just interrupt.
Yes, yeah.
There's a very funny story after the Second World War from a German scientist that had exactly the same idea, and he wanted to pay off the debts of Germany back then from gold and seawater, but the amount and the ways that you can extract it are not financially viable. But now, as we talk for bidding, for example, if we take scavenger resins, yeah, eventually they will fill up.
Well, this is the first question was a trick question, because in normal seawater they are very low, but now when we're talking about
Depends on
desalination,
volume.
they concentrate up.
Yeah.
And now that we're talking about brine squeezing and getting more water out of desalination plants, the concentration factor comes
Higher,
into play.
yeah.
So what we thought was the case previously may not be the case going forward. And now, because the volumes have decreased significantly, the concentrations have increased, it's a double whammy. Is it still the case that?
Well, I mean, it's a very, very small quantities, and I think if gold triples or quadruples in price, I'm sure it will become viable. But right now, at the current prices of gold, it's not yet. But it's possible, you know, with everything happening in the world, it's possible that gold and silver can jump in prices and they suddenly become cost effective. That's why one criterion we use in DTRI is multiplying the amount by the current market price, and that's how we kind of do a weight factor on what we consider is viable and what's not, because the two have a very important, you know, intertwined basis. Because it may be very small, but if it's so expensive, like Gayatri was showing about rubidium, it suddenly becomes very, very interesting, as long as you have the market for it. Of course, that's the other thing.
So just a thing on gold. Gold is kind of like the parts per quadrillion in seawater.
But that's one of the questions I want to ask. Is that everywhere in the world the same?
No, but
Some areas in the world
No, but-
high levels?
So the point I was going to make on this, which all comes back to the round and sort of ties back in with Chris nicely, when we do an analysis of seawater, we do it with the analytics are available to determine things that we can only see, and then anything below 5 milligrams a litre we forget about because we can't measure it. We need to look at the better technologies for identifying what these low concentrations are,
Sure.
knowing
And
that
they-
through our brine process.
and they exist, and you need a good person and a good lab.
Yes.
And you can buy them.
But also knowing that through brine processing, those concentrations are going to be multiplied maybe up to 2,000 times. And then, does it make sense?
If you have no losses in the system,
Yes.
right?
Yeah, and you know, and there is a completely different, and I would add that to your list of technologies that is coming, but it's not, again, I guess nothing valuable gets published anymore. It's a technology that you press the envelope of the recovery, because currently we're limited by scaling and by conventional anti-scalants to deal with recovery. So we limit it to 50, 60%, and then we suddenly are stuck. But there is a new set of technology that's being developed to bring the recovery in seawater down up to 90%. And we're not talking thermal technologies, membrane technologies. So that will shift. That is coming. It's just not published because it's too valuable to be published. So that is, I think, one area that we'll see a major breakthrough in very, very soon.
Yeah.
In terms of increasing what we consider recovery today being 40%, 50%, can technically now, and technology exists already, it's just not published information yet, go to 90% in seawater. So then many things will get concentrated, as you said, 10 times, 100 times, in terms of once you get to 90% recovery, that's basically 10 times of everything gets concentrated. So I think overall, that and I think the value of all metals, including gold and others, will go up as well. Because I do believe that as we see economic development in the world, the Middle East is wanted to turn into a high-tech world, part of the world. That is a huge amount of high-tech that comes in. That means wealth will be created. Wealth is nothing but gold. So there will be a tremendous amount of gold demand in the world because of the value that will be created that doesn't exist yet. So I do believe that gold will only go up in terms of value, just because the world is changing geopolitically as well.
Okay, so now I'm very happy to close this first session. So thank you for your valuable discussion together. Hopefully we will also combine all together. Also we have a video and then we will share. Then we will summarize and look at the next step from the first session. So now invite our second chairperson, Kayasri. She will sharing our second discussion session. Please, Kayasri, you can start.
Yeah, hello everyone. So in view of the limited time, I invite Professor John Lenhart to start your presentation.
Well, my browser is objecting to your URL. Let me see. Okay, it says it's very unsafe. I have a stick.
Forget it.
Let me just plug into a computer over here.
Yeah.
That's okay. There's only one slide deck in there, so. Yeah, that one.
This one?
No, oh, there are two slide decks, sorry. That's right, I used it yesterday. That one, yeah, good. Is there a clicker for that?
Yes.
Well, thanks.
Oh, marvelous, how about that? So, hi everyone. I'm John Leonhard. I'm not going to spend time introducing myself. This is a collection of things that we're doing around selective separations. As I've been sitting here, I've been putting things in and out of this, saying, oh, I should mention that. Oh, too much on that. I have no idea how long this presentation is. So let me see. Does the clicker work? Next slide, please.
Yeah, it worked until now.
Yeah, so we've been very interested in solvent extraction lately, both for water separations and for fractional precipitation. We just published this review article that is online now if you want to read it, where we've looked in great detail at the literature around this. We rounded up a number of people around the U.S. Our primary partner's been Aaron Wilson at INL. We also have Eve Prussia and various others who've been involved in this. So it's comprehensive on the subject. I won't say a lot more. Next slide. Generally speaking, with solvents, you can either recover purified water, essentially sucking water out of a brine into an organic rich liquid, then doing a separation over here, or alternatively, you can pull organic into an aqueous solution, changes KSB, and makes things precipitate out. Both processes are well known and been around for a long time. Next slide, please. So we've been very interested in, can I just get to the control here, in dimethyl ether. This is a liquid-liquid equilibrium diagram. And so generally we're working with two liquid phases in this substance. one that's organic rich, one that's aqueous rich. And dimethyl ether is very interesting. It is a nonpolar isotope of ethanol. And so we eliminate the hydrogen bonding in that phase, which is what gives it a lot of its interesting abilities. Now, there are a whole spectrum of solvents out there that have been used. There's been a lot of work at Columbia lately around the amines in particular. We like dimethyl ether, however, because it is, I'm not a PC person, you know?
You know, let me try to,
See if you can get that going.
do you have it in? Do you have the control
it's
component? Okay.
One click here would be perfect. Oop,
Okay, it works.
except that it doesn't keep the animation. So, in
Oh.
any case, if you look at dimethyl ether, it's the curve up here. It has two characteristics that are really lovely. It's got a low enthalpy of vaporization relative to water, and it's got a very high vapor pressure relative to water, which means it's fairly easy to separate out by pressure reduction. And that gives it some particular value for these types of processes. Now, here's some examples. These are courtesy of my colleague at INL, and some of the things that he's managed to separate. He's been interested in both salts, gypsum, and in particular rare earths and lanthanide elements that you might find in battery leachates. And so one of the big problems we're facing now is how do you recycle spent lithium batteries and recover those rare earth elements? And this material has that potential. Here's some more detailed things, again, on the battery leachates, magnet leachates rather, samarium cobalt solutions, neodymium iron boron leachates, and they're able to pull out very high concentrations of the lanthanides in particular from solution, which gives it a lot of value for rare earth recovery in these types of systems. They have a perspective here in Nature Communication that just came out. So in terms of the modeling here, we've done a lot of work on the thermodynamics. I won't spend any time on this, but we have been interested in trying to model the excess Gibbs energy of dimethyl ether and water. The data sets are relatively limited around this, but we've been fitting various components, various equilibria for which we do have data, and then using that to construct expressions that reflect isoactivity and isofugacity conditions in these liquids. We've been fairly successful, and we published this work recently. Some of it's in the Chemical Engineering Journal, citations missing here. Now, some other things that we've been up to. We've been looking a lot at using NF for separating monovalent, divalent, and hypersaline brines. This is particularly around, this is work that we did in the context of the geothermal lithium extraction challenge. It was recently run by DOE. And one of the things that we've looked at is how rising salinity tends to lower the selectivity. We've also been very interested in pH optimization, finding generally the best selectivities at low pH and low TDS for this type of work. What's going on here? Physically, what we think is happening is that as you move to higher concentration, you're getting more ion pair formation. Low concentrations, the lithium and the chloride might be by themselves. Then they start joining up as the concentrations rise. Magnesium and chloride, again, starting to form ion pairs. And that begins to interfere with the monovalent divalent separation. The other mechanism that's been proposed recently by Ritt, I believe out of Yale, is that at high concentrations, the Debye layers on the inside of the pores become thin. As you know, the Debye layer thickness drops off with concentration. And when that happens, stuff can slip through the middle that is not so readily able to do so at low concentrations. Let's see. We've looked a lot at the Donan steric pore model for modeling NF membranes. We spent a lot of time looking at these particular methods of predicting selectivity. And by using mechanistic global optimization models, we've been able to reduce the data requirements for making those kinds of fits. This is a 4-component solution, and our model compared with data by others. And you can see we're able to represent things fairly nicely. This just appeared in JMS a couple months ago. So again, we're feeling pretty good about the use of advanced numerics to extract the parameters. What this does in particular, typically when you fit NF data, you take some data for an uncharged solute and you infer the pore size. And then you go back and take another data set for a charged solute so you can start dealing with the dielectric properties and membrane charge. We're able to get this all from one data set, just working directly with the charged material. Salt was mentioned, so I thought I'd mention something we did on salt production. This is, I didn't come prepared to speak on this, but when Nikolai mentioned it, I threw this masthead up. We did look at world markets for salt production through RO and ED, and as Nikolai noticed, it's functional where you are. If the place has got native rock salt, it's cheap. If they're sending it in by ship, it's expensive. And that's really the market force behind it. The concentration of dyeing, I wanted to note the thing that we did here with Jay was to actually replace the sodium chloride by sodium sulfate. And that gave us a big advantage in using NF to recover the dye bath water rather than having to go to RO. And so this was a neat little paper, field tested actually in Erode in Tamil Nadu in one of the textile mills there. There was mention of producing membrane cleaning solutions. We've done some work on both direct electrosynthesis and BMED to look at caustic production and or hydrochloric acid production. We kind of laid out the processes you could use. We're not specifically pursuing the implementation of this, but it's there for those who wish to. And that's it. That's what I have. Yeah, please.
The DME solvent or anti-solvent is very interesting. It's also very explosive. How do you foresee that going on a large scale in industry?
Well, the process that's being realized right now by Trevi, who's one of our partners on this, really involves taking industry standard precautions for handling it, which is a separate structure with appropriate ventilation and fire security. But to your point, can I pull this out?
Yes.
To your point, solvent extraction has gained a new life, and it's being used very heavily in the U.S. now, commercially, for the cannabis market. As you may be aware, the United States has decided that pot's okay, and it's been commercialized.
And many other countries as well.
Yeah, and many other countries that some of you may be from, and countries that you're in that may still take it very seriously. But in the U.S., it's become an enormous trade market. You can buy these solvent extraction systems, and in fact, very quietly, my DOE partners bought one from one of the pot companies in order to use it for tests at INL. Now, these are people who undergo randomized drug testing. So, you know, they're not smoking pot. But the fact is we have trade shows with 60,000 people at them for that kind of technology these days. So it's coming along. And their solvent is often ethanol, though.
Yeah.
Sorry, Professor, just add on that. Typical latex design, you're good to go. And the thing is, with the solvent extraction methods for brine treatment, is that I know of two,
Yeah.
and both include flammable
Yeah.
solvents, right? And I personally done a proposal for one of them for a project, and yeah, it's easy. Once you get to know what you have to do with the latex design, it's easy. The point is getting there. And for us who don't know, yeah, it sounds difficult, but for people who work oil and gas, it's pretty easy to be done.
Yeah. Yeah.
Thank you.
The oil and gas has been dealing with these types of highly flammable substances for a long, long time.
Yeah, exactly.
Thank you. I guess we'll take more questions later.
Okay. Thank you all.
Thank you. With you next.
I was just in town, didn't it?
Yeah. We just fixed the slides.
I think everybody here was at the IDA, so I'm not going to do the what is neon thing. I think I'll talk about a few things that have not been talked about before in terms of the context of what we're doing and trying to deliver. So first slide, I've just cobbled this together, so it's not as professional as perhaps it should be. But this is the results of ongoing seawater analysis that we've been doing on a monthly basis for the last 3 years to give us, that's what we're dealing with. How do we remove these to let us work? 500,000 cubic meters of water supply for NEOM for something like 9 million people by the year 2030. That's my job, to deliver water. The solution is in this room, to do that without discharging any brine, so I won't go over that. I put that together because I thought it was interesting in terms of those concentrations and how relatively they compare to each other. So it's all sodium chloride, and then at the top. And then my next stage of this slide, which I didn't get time to do here, was to actually rescale these against the values of these products. Which I will do and present later. But this is the infamous slide. So I came up with this in my first week in NEOM, went to a salt conference in Rotterdam, and they were all talking about the different salts and where they all come from. So I started to draw these around where brine comes from and what the pathways are, what can you produce. The interesting one that's missing is sulfate, because sulfate can come out in many different forms. So this is what we did, and then we got to producing this list of products that we could produce from desalinating 500,000 cubic meters, how many tons of each one there were, whether there are markets for them, etc. And it went on, but I'll skip through this and we'll get to the interesting stuff. So then when we looked at that in terms of chemistry and those products, this is the process flow scheme. This is the complete integrated recovery of all products so that everything is used and we don't discharge anything to the environment. And I purposely don't say the phrase zero liquid discharge. It's complete recovery. It's not discharging anything. So it's quite simple. Desalination up here. The big question mark box about how do you link together providing people with high purity and high concentration brine with desalination. If you go to somebody in the salt world and say I have 250 milligram per litre concentration, quite high purity sodium chloride, is there anything you can do with it? They'll say, don't be stupid, that's what we use all the time. It's just linking this bit with those people so that they're going to be able to take it. So in terms of the process flow diagram, nanofiltration gives us a monovalent stream and divalent stream, polyvalent stream. Gypsum, magnesium chloride, eutectic phase crystallization, magnesium hydroxide, through to magnesium oxides and magnesium metal, gypsum mod production. We've just been talking about all this. Nothing of it is new. It all exists within the world. The big challenge is putting it together as necessary. That's what the actual process flow stream looks like with all of the various purge streams and return streams involved as well. So it's quite complicated.
It's complicated.
Yeah. That's it simplified again, just in terms of the evaporators, the boric acid recovery, etc. So this is the scheme. This is where we're at in terms of our progress. The desalination portion is based on what we've been talking about. Nanofiltration front end, a fairly conventional middle stage that will be quite interesting in that it has NF and hence has scaling potential reduction in that reverse osmosis stage, and then as high a recovery rate as possible to reduce the thermal load in evaporators downstream. That currently sits with CDEM, who are the joint venture partners that we have, and CDEM are looking really at the technology, what can they adapt to put together an EPC package that can actually be going out to the market and somebody provide guarantees, because we have PIF and all of the joint venture and the finance people sitting there saying, this is great, but it will work, won't it? You know, that there's no risk involved in anything that we're doing.
Zero risk.
There's zero risk, because it's all proven, all this is proven technology, so it's no problem.
Yeah.
So that's the balance, and one of the reasons why I made the comment I made at the Leaders Summit about the business model for developing these is the biggest obstacle that we have to implementing innovation. The RO stage, it was simple, so 3-stage NF pre-treatment to give us a criteria that we set as being a magnesium ratio relative to the polyvalent stream TDS value of 0.35, and on the monovalent side a sodium ratio relative to the monovalent TDS stream of 0.12. Those are what we believe through looking at the projections and talking with people like DuPont we can actually achieve in terms of the degree of selectivity that's possible. Then the other big question, energy to do this. Evaporators, crystallizers, we are something like 2.7 gigawatts. When we show this to our energy people in NEOM, it's like, that's more than the rest of NEOM put together. Great. Where are we going to get all that from?
It's a large
renewable
nuclear power plant.
Yes. And also as renewable power. So majority of it is going to be solar, so we have intermittency of supply, base load, all of these issues to drive. So pushing things as far as we can with membranes to get as higher recovery rates as possible, all part of what we are currently trying to assess and figure out and move forward and bring the business models together for. That's basically what it looks like. The desal plant is there. The brine processing on the other side of the street are all these areas of what we've figured out as being the required footprint for each one of these unit processes, and then integrating them together as well. So putting gypsum, unless somebody's moved it, gypsum should be over here, because gypsum's going to precipitate and we've got to put a pipe over there. This is like the infamous hydrogen plant that everybody knows about. And so within this region, this is where we are with the plan. We realise, everybody keeps on telling me it's really ambitious and really adventurous try to do this, so we need some sort of proof of concept, we need some sort of innovation and development, or when we present this to this board, we call it a demonstration plant, because there's no risk, because it's all technology that already exists in the world, so all the backers should be fine. But the innovation, if I go back in, that was the hydrogen plant. The innovation centre is going to sit within this region here. I'll come back to that one in a second, but it looks like this. Interesting story. This went through the great and the good of the architects within NEOM that needed to really understand and give a strong message, and they came back about a month later and said, well, if it's a water innovation centre, make it look like a bubble. So it looks like a bubble set
Or a big button,
and a
like
big
the easy button on
It
the Target commercial.
Yeah, so it's a big flexible space with room inside to bring skids in and out. It has all of the tankage in the basement layer underneath to make the building as flexible as possible. And it sits here. And then up above it is going to be all of the unit processes for proving out each one of the brine processing and material recovery processes. The interesting bit, the bit that I didn't talk about, we all talk about zero liquid discharge from desalination. That applies to every industry within NEOM. So a hydrogen facility that would normally take water for cooling cannot discharge that water back into the ocean. So they can't use a single cycle or straight through seawater cooling systems as you would normally do, because of the temperature difference and because they would add some corrosion inhibitors into that water and therefore not allowed under the policy. So then we got to thinking, everybody keeps on telling us all the money is actually in the brine processing, not in the water desalination. So we have an intake, pre-treatment, NF plant, send monovalent brine to a seawater cooling tower with a 2 times concentration cycle on it. That comes back to us to a OARO or brine squeezing type of facility, and that brine goes to brine processing. So as well as reverse osmosis and dewater salination, we have the first industries that are using seawater cooling with ZLD. Yes.
Just quickly, what temperature is your monovalent stream coming out of your cooling towers?
It's coming out at basically the same temperature as the cooling tower, but it's got a 2 times concentration cycle.
Okay.
Yeah, because it's the latent heat that you remove out of the cooling
The
tower.
same temperature as the cooling supply.
Alright.
Because the water is already evaporated, and the evaporated water gives you the cooling.
Yeah, it gives you the cooling, yeah, of course.
It's a blowdown from the cooling tower.
Yeah, sure, that's right. You just don't want to overheat your membranes and
Correct.
ruin them.
Yeah.
That's all.
Yes. So yes, that is the NEOM scheme, and the Innovation Centre is growing quickly. This building is out to tender, it is actually happening, and we're looking forward to figuring out how this centre is going to be able to collaborate and take ideas. What we're really aware of is that this is version 1. It is the first 500 MLD of desal capacity with a total capacity of around 2,000 MLD of desal for a population of 9 million people. It all sounds crazy. Anthony was saying that the line, the infamous line, they've started to clear the top of the camp because it's coming. And so there's a huge degree of commitment to deliver the project and obviously to supply water.
Just a quick question. I don't think it was discussed. How much of the percentage of the water that you will create as a drinking water, as a desalinated water, how much of it will be used for municipal and how much goes to industry? Do you have a sense of?
It's about half and half. So not industry. Well, say thirds. About a third of it is used within food production, a third within industry, and a third for
municipal use.
Municipal supply.
Okay.
One more question. So let's just say what happens when your hydrogen plant goes down.
Yes. So that's why this facility used to be part of the large desalination plant. And I've separated it. So this can stop.
Yeah.
And also, if the desal plant has a problem, this can have redundancy to ensure that it still supplies cooling to the hydrogen plant.
They wanna use the water split electrolyzer, or you mentioned briefly about chlorine-alkaline electrolyzer. So what kind of the device to generate hydrogen?
Oh, within here is an electrolyzer, ThyssenKrupp Air Products electrolysis. Yeah. So I have frustrating comments that my thermal processes here will produce quite high quality water.
Yeah, makes sense.
But they weren't connecting through the municipal supply, so it's only when you actually get to the engineers who say,
You wanna use the thermal-based water product,
yes,
not RO.
yes, yeah. If we keep the lawyers out of them. The lawyers just want connecting into the municipal system and say thank you very much. There's lots of very different challenges. Hence, I'm getting fat and going grey. So yeah, that is.
Potassium that's being separated?
Sorry?
Is it potassium that's being separated in that little box thing? After gypsum? Yeah, potassium, yeah. So as the potassium chloride, is it a potash? Oh yeah, so it's a potassium chloride. Okay, all right. No, this potassium chloride recovery, then it goes to, all right, okay. So is that a chemical precipitation?
I'll have to zoom in now. Potassium chloride. Maybe a eutectic freeze stage as well. I'll have to check. I can't remember.
Okay. All right.
But this is where I say when we've done all this, here is lithium and rubidium.
Yeah,
recovery.
yeah, I
The
can
amount
see
of
that.
concentration at this step is just enormous.
Because it's interesting that if you've already recovered the potassium at the point, then it's
Yep.
easy to get the
Yeah.
rubidium.
Yeah.
That's
a good way to
wondering
go. Yeah.
how did you do that and still get the rubidium? Because from analysis, the potassium, at least the rubidium always goes with the potassium. So I was just wondering, how did you separate it?
What we also talked about a little bit earlier as well is doing all of this in one go is going to be impossible.
Yeah.
So some of these, what we will do is just leave as impurities. We'll feed them back into some of the products that don't really care that they're there.
Okay.
So within some of the salt offtake, if that salt offtake is going to de-icing industries, they don't care. So we've got a degree of flexibility. We also look at things like sodium sulfate instead of calcium sulfate, potential link in with the glass industry. There's all sorts of different options as well.
Okay. I guess Thank you.
Oh, I did get some applause. I thought I was the only person who was going to get
Okay, Professor Sean, you're next.
Sorry, from my side, ladies and gentlemen, I'm sorry I have to catch my flight back to Amsterdam. So I have to bid you.
Thanks for
Thank you for coming.
Well, safe travels home. We'll be seeing you soon.
Exactly. Thanks for organizing this.
Safe journey back.
Safe trip.
So I'm very happy to share that our resource recovery activity in terms of research. So we have collaborated with the Qatar University as well as IIT. So we just want to share some of the progress. So we have developed the electrochemical process to recover lithium or some of the rare earth elements. So this is our concept. We try to capturing specifically lithium compounds. So we have selected CDI. The CDI is one of the growing technology. So you can have a graphite electrodes. Also we have carbon electrodes, and then we can also combine some of the ion exchange membrane as well as the MOF or COF, which is selective on your ions material. That's the reason why, based on our previous literature review, GIF8 looks like a very interesting MOF material because they have a specific channel can selectively lithium can pass through within their structure. That's the reason why we try to coat our GIF MOF material on the top of the electrodes, and then we also look at the ion exchange membrane. So if you have a plus charge and minus charge, so this CDI can selectively 50% ion can specifically you can recover. That's the reason why lithium is plus charge. We utilize a cationic membrane. So 50% of the cationic ion we can deal. We don't have to deal all the unnecessary anionic compound. That's the reason why we feel electrochemical is much better solution if you want to have a selective ion recovery system. So this is the activate carbon, our electrode, and then this is the we try to grow the GIF MOF material on the top of the activate carbon, and this is the GIF-A coated electrode. And then we also cover cation exchange membrane on the top of that, and then you can see the same image of what's the recovery ratio, how we can make a different selectivity of the lithium ion. So this is the result. The lithium recovery only electro activate carbon, and then we put the GIF MOF material also only cationic ion exchange membrane and GIF and cationic membrane. So how selectivity can be changed in terms of sodium, potassium, magnesium, calcium. And when you have only the electrode activate carbon, the selectivity of lithium to metal ion, so sodium 0.7, 0.4, and 0.5. So most of them are less than 1. And when you try to coat with the MOF, then we have increased the significantly sodium and lithium selectivity, almost 3 times higher. And then potassium 1.12. Then when you combine only ion exchange membrane, still the efficiency is not as good as MOF material. But when you combine MOF, GIF8 and cationic ion exchange membrane, so we have a high selectivity 1.38. So that's what we have progressed so far based on this kind of promising result. So we want to try to also increase the level of selectivity of lithium and then some of the material based on our MOF and COF, also cation exchange membrane. So we can combine together and selectively remove our targeted ions. So that's our progress. Also, this is the Sydney seawater composition. So you can see very much similar to in general like a Pacific Ocean. The 35 gram per liter, 3.5%. the calcium, magnesium, potassium. So what we are interested in the fertilizer. So one of our interesting target is the fertilizer recovery for a circular economy. If you see the potassium, already people try to recover potassium almost 400 milligram per liter, and this is the one of the fertilizer from seaweed. So we have a lot of seaweed in coastal line in Australia, and they just grind and then extract the calcium or some of nitrogen, phosphorus. So utilize as a fertilizer, as a biofertilizer. So you can buy $100 for almost 10 liter. So 1 liter is $10. So you just collect the seaweed because they absorb a lot of potassium from seawater. So seawater potassium concentration. So this is the potassium-rich fertilizer from seaweed, and then we want to look at the nitrogen and phosphorus. Nitrogen and phosphorus are very important fertilizer. So if you see the nitrogen concentration very low from seawater, even phosphorus concentration is almost zero. So how we can get the nitrogen, phosphorus, which are the most important fertilizer compound. So we want to combine also wastewater as a nutrient in a circular economy system. So wastewater contain a lot of concentration of nitrogen, phosphorus in domestic wastewater, industrial wastewater, even animal, livestock wastewater. So we want to process the nutrient-rich wastewater so that we can collect this nitrogen and phosphorus and then mix with some of the extracted potassium and then magnesium or calcium. They are all fertilizer in seawater. So we can make some kind of refreshment of our necessary combine the whole fertilizer. So wastewater, we are talking about only seawater, but also we can make sure some missing component from the wastewater, which are very high concentration of nitrogen and phosphorus, which will be a good fertilizer solution. So if we combine seawater brine as a resource recovery as well as the wastewater as a resource total nitrogen phosphorus, so that will be also a good combination to grow our food. And then it will be also, as usual, like a seawater desalination, wastewater, we are the indispensable relationship for last more than decade and then for 100 years. So it shows a good timing. We are also look at some of angle from wastewater, seawater brine, as well as the wastewater brine, even recycling brine, or just as it is from your primary wastewater. So it will be also a good opportunity. We have developed this technology to look at also fertilizer recovery system. So that's what we are working on for resource recovery. Thank you.
Any questions?
Just a general comment. I mean, the opportunity to recover the three nutrients you mentioned in a more sustainable way is a very significant one. Most of our ammonia today is produced by the Haber-Bosch process, which burns natural gas fundamentally. It consumes 2 to 3% of world primary energy. Most of the world's supply of phosphate, about 75%, is in one country, Morocco, and controlled by the company OCP. Most of the world's supply of potassium comes from mining in the northern hemisphere, and to get it to places like Australia, that means transshipment from the far north down to here. And most of those resources are controlled by a small handful of companies with monopolistic pricing.
All right, that's very good
So
point.
we're in a good business then.
That's true,
If you want to get shot by monopoly companies that don't want you breaking into their monopoly.
Well, we could be monopoly men as well.
The fertilizer market is $160 billion per year. And then if we observe the sum of the fertilizer from the seawater brine as well as the wastewater, already John mentioned about what's the energy cost we can save from the Haber-Bosch process. Also, we can think about recycling reusing this nutrient from the wastewater or some kind of waste material. And then we can observe around 10% of the nitrogen and phosphorus, which means almost $16 billion of a market we can observe from this
One question I have is, have you started looking at kind of a joint desalination and reuse where this was tried in by the Japanese, where you have a wastewater plant and a desal plant next to each other. They do this for industrial wastewater treatment because of not being possible to use the water for drinking purposes. But they will take the seawater RO brine, not seawater, but brackish water RO brine from the wastewater plant, and then feed it as a feed to the seawater desalination plant, which is, although this brine is high salinity, it is like 4,000 or 5,000 TDS versus seawater being much lower, and it actually adds this phosphorus and basically the two nutrients you mentioned, nitrogen and phosphorus, because this is actually very rich in nitrogen and phosphorus, feeds it into the seawater, so you end up with a brine that has everything in one place, versus what you have. And that is kind of how the Japanese are looking at solving that lack of nutrients of nitrogen and phosphorus in desal. Have you looked at any processes that you guys are exploring here, research-wise, to basically use because when we talk about zero liquid, like in our case where we have industry that's an industrial wastewater and we recycle, and then now we have concentrated brine. That brine is still low salinity. It can go into the seawater feed to reduce it, but at the same time now we have a different brine that comes out that actually could be very valuable because it has everything in it. It's the complete complete nutrient set.
In fact, you are right. Our salinity desalination, they are co-located together with the wastewater reuse plant. So they discharge to our ocean, have the brine and then the wastewater, also some of the primary treatment system. So that's also possible because we look at the RED and then PRO because low sewage effluent and our brine combined the salt gradient.
That also can be used to
That's the reason why we look at the opportunity, but definitely it can be also possible look at the fertilizer prospect of the view, so that we can also look at
solves two problems at the same time. No more industrial waste discharge, and then now you have a brine concentration, with the full set of nutrients in it. So
we try to also look at magnesium from the RO brine seawater desalination and then put into the wastewater, create some of the strobite, ammonia phosphate, and the magnesium can be generated from your anaerobic digestion supernatant as well as your wastewater effluent. So that we try to also look at extract from magnesium seawater RO brine and then produce the strobite from wastewater nitrogen phosphorus we can also capturing. So it was also one of our interests to combine together as a fertilizer business.
Sounds very good.
One more question.
A quick question. On the fertilizer industry, and if we take potassium as an example, is there a preference to which anion is associated with potassium? So is potassium chloride the same as potassium sulfate? Is the same as potassium carbonate? Is the same as potassium nitrate? Might be a little bit more valuable because there's the extra nitrogen in there. But the fertilizer industry, would it not care in which anion comes with it, as long as the potassium is there?
That's a very complicated question because even ammonia is the most important fertilizer, but some people provide ammonia as ammonia chloride or ammonia nitrate or ammonium sulfate. You're right. So depending on your counter ion, so your value of the fertilizer differ, very much significantly. So that's the price issue. Some of the farmers, they want to buy ammonia chloride because it's cheaper than ammonia nitrate, even though ammonia nitrate is the better performance, more nitrogen, but for their plant, it doesn't really make a difference. So that's why the farmers select ammonia chloride, also they purchase phosphate and then necessary some of the micronutrient, calcium, magnesium, iron, something like that. and then they can utilize. So you're right. The potassium nitrate, potassium chloride, potassium sulfate, they should have a function of this because sulfate is also very important macronutrient. Sulfate, also nitrate, potassium nitrate is nitrogen phosphorus, but depending on your crop, depending on how much you, also depending on your cost. So farmer will decide, okay, it's better to buy this kind of combination of your counter ion. So I cannot say which one is correct, but it can be selected by the farmers.
And one other that we have to be conscious of, potassium nitrate as a substance is controlled in Saudi Arabia.
Okay.
So we have to.
You could blow up stuff with it.
I think Beirut.
Am I so?
Yeah, one level.
I,
Yeah, yeah, yeah. You had one question.
I was just gonna comment that chloride and sodium are toxins to most
Right.
plants.
That's true.
And, if you start fertilizing with those, you risk salinizing the soil.
Right.
Particularly when that's all you use.
Yeah, especially if it's drip irrigation on top of it.
That's the very important issue because we also look at the toxicity of the sodium and chloride, and then there are some specific plants like a vegetable like a lettuce. They are very specifically toxic of sodium, but when you look at the turf like lawn and there are a lot of golf courses, you don't need a very high quality of fertilizer. So we target you don't have to be very high purity, high quality of fertilizer. That are already good enough to grow your lawn and turf that you can utilize. So we don't have to produce very high purity of fertilizer. It's enough. And then as long as they can grow in the golf course and you can save a lot of, and the resource recovery can happen. So we have a two category. Okay, high purity of fertilizer and then middle quality and then low quality can be depending on the
I guess
farmer.
it depends on kind of follow the money principle. Basically, when you go out to the fertilizer industry, they have different prices. So you would want to make whatever sells at the highest price, as long as it doesn't cost you much.
Absolutely.
So I would say price in this case would drive what we offer the public, as to say, or the users.
Yeah.
So, but that's very interesting. I mean, in Florida, we actually, for now, the last 4 years, we have a ban for discharging anything to the ocean. I don't know if you know that. It's an interesting experience because my company has done made a lot of money out of it. And the way we deal with it is because most of our plants are brackish. We have only one plant, Tampa Bay Water desalination plant. All of them are brackish. We would, and they are mainly calcium and magnesium TDS. I mean, 80% is calcium and magnesium in the TDS of brackish plants. So what we do is we combine the wastewater stream with the brackish brine, mix it together, and then we use 100% of it as for irrigation purposes. So we have a complete net zero discharge. We just use everything, and that kind of a thinking where you're supplementing, as you said, the wastewater nutrients and one carrying you the calcium and magnesium, the other one carrying you the phosphates and the nitrates. It works perfectly well, and it actually it's a proof in now been enforced in Florida for 4 years. It's a proof you can do it. Actually, it exists. It can be done, and by that concept, put the minerals together, and that's right. Now we're starting to look more into the supplementing by joint desalination reuse, starting to send the brine from the industrial facilities into the feed water of the seawater plants. That is. Has its merits as well. So, there are a lot of things like that are happening slowly.
I think so.
Thank you. Professor.
Thank you, excellent. You guys are doing a lot of interesting work.
Dr. Hamid Yunus.
Does pointer work with this or not?
Yeah, it does. It just let's see.
It's
but
a different computer.
It's a
so-
different
Oh, it is. Did you plug it? Yeah,
Do you
put it
want to
in.
plug this
Put
one?
the USB. You have to
Yes.
put the USB in,
Yes.
and then it will work. I mean, it works on every computer, Mac or non-Mac. Okay.
Okay,
It
super.
does.
Thank you so much for giving me this opportunity to talk with you. Very, very brief introduction. My background is chemistry. I'm looking at everything as a chemistry point of view. but currently I'm working at Petroleum Engineering Department, and mainly oil and gas, anything related to chemistry, we are very active from the corrosion scale, those things, we love it. But I have a very personal interest for many years that try to recover valuable minerals from the waste resources. One of the abundant waste resources that we have in oil and gas, we call it produced water. We have a water that only in Texas, in the West Texas, we produce 3 million cubic meter per day. That's a significant amount of the water that we have to dispose it in the same day in another well. We cannot spread on the surface. That water has at least 15% salinity. It, most of the case depend on the oil wells or gas wells. In the gas wells, we have up to 37% salinity. The ratio of the sodium, potassium, calcium is very different from the well to well. And almost all the ions that maybe we know is possible to find in that water. We have it depend on the well and depend on the position. Sometimes we have a radioactive material, a significant amount of radioactive material, but at the same time, we have a significant amount of the rare earth elements. Sometimes it's 6,000 times more than common seawater. For example, we now for the United States, we have like a map that we found that where do we have lithium, where do we have rubidium, cesium. In some cases, we found that we have some water in the United States with a 30 ppm cesium, 40 ppm rubidium.
That's amazing.
And in some cases, even for lithium, we found that some places 600 ppm lithium. That's a significant, just without any evaporation.
Any concentration.
Just naturally, we have a huge amount of very rare earth elements.
So you gotta
At the
get
same-
into the oil business then.
Doesn't quite fit the narrative.
And also, we should consider that usually for each barrel of the oil, on average, we produce between 4 to 10 barrels of the water. We have a water industry instead of oil industry. But usually oil industry, they don't want to talk about this water because it's very saline and
It's the dark
contains,
side of oil.
yes, also contains significant amount of crude oil. This water is not like a common water that you can see in desalination, but it's a very common water that you can see is very black, contains significant amount of H2S. And all the time we have a solid material, some oil. Treatment of this water is a big challenge. This is one of the reasons that I prefer to working with a more challenging water. If we have a very hard challenge, therefore, after finding the solution, we can transfer that knowledge to the simple challenges like brine that coming from the desalination plant. But how can we do that? The most important things in our study is scalability. Most of the things that we can use for recovery, lithium, rubidium, cesium, they are not scalable. Look at the 3 million cubic meter per day. We cannot use any polymer. We cannot use any metal organic framework. We should have a very real solution that would be scalable. That's one of the reasons that we concentrate only to a scalable solution that is very easy to do, not fancy things. We already studied many different kind of adsorbent polymer things, but at the end of the day, going nowhere. Is it just that one publication add to the other publications? It's not industrial. It doesn't have any industrial value. And I have one thing in my mind. I try to take a lesson from the nature. Usually in the nature, we have some process that over millions of the years, some things happen, and we know that, for example, how potassium move, how sodium move, how lithium move. And if we carefully check some of the natural phenomena, maybe we can take advantage of that process. For example, we know that milk is able to grab some of the heavy metals. We use same technology. We develop some sort of we extract some proteins and chain of the amino acid from the waste of the cheese industry. Because they have water, that water is useless for them. We have some protein that can selectively grab the entire heavy elements, radioactive material from that water. We have more than 99.7% completely removing the uh, radioactive material from that water. At the same time, for grabbing more potassium, calcium, magnesium, we try to use some sort of the polysaccharide. Polysaccharide, they have a tendency to somehow attach to the potassium, magnesium, calcium. By this attachment, they work like a sieve now. This kind of process, they are scalable because we know we can have thousands of tons every day of cellulose, ketone, or most of the polysaccharide, they are naturally abundant. We can have it, and we can, with some sort of chemical modification and functionalization, make them very selective toward just one ion. What we have, when we introduce such a salty water to this system, only sodium and potassium coming out from this adsorption. And most of the divalent and trivalent things complete trap in the system. We try to develop, not stick only to the adsorbent system. And one thing that all the time we keep in our mind, one size never fits all, because each well has a specific water composition. We have to functionalize new material to be very useful. At the same time, sorry, we would love to have like a very general procedure. Therefore, we move to something else. We know that we have a huge amount of CO2, and these days we have some interest for the CO2 capturing. Now, in Texas, for each ton of the CO2, if we sequestrate, government give us $50. A state like California is about $80 per ton, and most of the country, they have it more or less similar things. We can somehow sequestrate the CO2, or using the CO2 for, again, trapping in the underground as for oil, enhanced oil recovery. But what I love to do, some carbon mineralization, because in this case, we have a huge amount of CO2 that we can use it for something else. If we have a waste, like produced water, at the same time, we have a CO2 as a waste, I can say this is the one stone, two birds. We have it, just we can consume both waste. What we have done, we are able now, for example, in the case of sodium chloride, in presence of a CO2, in ammonia as a catalyst, we can have the baking soda or sodium hydrogen carbonate plus ammonium chloride. Or similar things for calcium chloride, magnesium chloride. In presence of CO2 and water, we can have calcium carbonate, magnesium carbonate. And we are very accurately able to forming very specific form of the crystal of, for example, calcium carbonate, calcite, aragonite, or playing with the reactivity and crystal size. I think this is the one of the best method that is scalable. Now we can have zero discharge. It's not going to any form of the desalination or membrane, or so. Just bubbling CO2 inside the water. We can, based on the solubility, separate them. But this process is not new. CO2, we know that CO2, even for millions of the years in the ocean, CO2 in presence of calcium producing calcite. But the point is the solubility of CO2 is maximum 0.1% in water. What we develop, we are able to making nanobubble of the CO2 and now tune the system. We are able to dissolve more than 7 times of CO2. We change the equilibrium of the carbonate to bicarbonate and CO2. At the same time, we are able to tune the mass transfer. The mass transfer of the nanobubble is 11 times more than the common microbubble. At the same time, if there is no cation in the system, we can keep the CO2 up to 7 days without any reaction. That's it. We somehow force the water to have the more CO2. When we have a more CO2, we can somehow change all the equilibrium and selectively, because of the solubility difference, step by step precipitate all of them, and now we have a market. The price of the sodium bicarbonate is 5 times more than sodium chloride, plus the amount of the sodium in sodium bicarbonate is half of the sodium chloride. If we have it, let's say, $70 per ton of the sodium chloride, it's about $300 per ton. and this is the zero because we don't pay anything for water. We don't even, oil company give us money to use that water. Also, they give us money to use the CO2. For sure, all the salt would be for free. It's very cash positive process. We try to develop and somehow optimize all the condition to one by one precipitate out all the salt that exists in produced water. And it is just a general scheme. We have a produced water with some sort of process. We try to remove all the valuable and let's say more abundant and less abundant mineral, and eventually we have a one water that we can use it for irrigation, that again with the help of CO2 we have CO2 sequestration, or we can use it for fracturing. For each well in the United States we use 5 million barrel per day, and each day we drill 300 wells. That's a huge amount of the water that we use the fresh water. If we have that water that we can use it or reuse it for fracturing, again, is a big saving of the water resources. Thank you so much for giving me this opportunity.
Yeah, this nanobubble concept is very interesting, but once you create the nanobubbles, you said it, obviously they last longer.
Yes.
But what happens after 7 days? You basically start losing them back to.
Let's say in a
because
up to
I mean,
2 days.
how viable this is for carbon dioxide sequestration?
I can say if we have one of the things that at least I have in my mind, we have a water disposal well. Instead of sequestration underground for some, let's say, geology things, sequestrating CO2 inside the water disposal well. As long as we have ions, this reaction is instantaneous. When we don't have any ions, yes, after a couple of days, I start to release and make it like agglomerate all the bubbles and make a bigger bubble and release. But as long as we have the right cations and also catalysts, for example, in the case of sodium, we can intentionally diffuse the ammonia in the system and converting sodium chloride to sodium bicarbonate. Same things for potassium. Same things for lithium.
Temperature makes a difference.
Temperature, of course, is solubility, but the point is, even at room temperature, we have a significant difference between solubility. Solubility of magnesium carbonate is almost 100 times less than, calcium is 100 times less than magnesium. Sodium is 100 times more than magnesium. Even these three, when we have 100 times solubility, at room temperature, we are able to separate them. We don't need to, again, consume some energy for make temperature.
What is your sense of how much energy we need to create nanobubbles versus the typical microbubble size, like a couple micron size versus nanobubbles? What are we talking about as far as size goes?
Yes, the size is about.
Will be half a micron.
Yes, usually the average size that pump that we have is about 400 to 500 nanometer.
Nanometers. Okay, so about a half micron. Okay.
Yes, but to be very honest with you.
I mean, I'm just wondering.
In terms of energy consumption, in terms of this is completely out of my area. I don't have that much.
Yeah, because obviously it has advantages that you mentioned, and it allows you to conduct those reactions and eventually sequester some of the carbon dioxide into products that, if you maintain the pH of the water, let's say like at the drinking water level, 8.1, 8.3, those will be all dissolved.
Yes.
They'll be almost 100% dissolved. So you could say that now you've sequestered some of those CO2 into things that are, we had that. We actually had the California guys from the Department of Health Services accept that, and because they asked us the question, okay, now you use carbon dioxide, turn it into bicarbonate, keep the pH at 8.1, so it is all dissolved. So therefore, we accept it as sequestered. But what happens next when I drink that water? We had the discussion that drinking water is not like, this carbon dioxide is not like alcohol.
Yes.
It doesn't necessarily.
We prefer pH reach to about 4.5, about 5. In this case, we are sure that we precipitate all the salts. Even if we don't have interest for separation, if we have, let's say, a very rich brine, only bubbling the CO2 and presence of some ammonia, we can precipitate everything. We have just the pure water now. If we have an interest for separation, yes, we have to tune the system, check the flow rate, pH, everything. But if we don't care, like a water disposal well, we can simply bubble the CO2 and everything will precipitate out.
So what is the secret in creating nanobubbles? Is it the nano, tubes that create them, or what is it that makes
To be
it?
very honest with you, I don't know the details. It looks like to me we have some sort of nozzles that push the CO2 inside the water constantly and producing the.
Is that a
other side.
commercial product?
Yes, is the pump, everything is commercially available in the even big size, maybe 100,000 liter per hour is available, those kind of pump. But usually they don't use for CO2, usually they use for oxygen,
Yes.
for making nano ozone or nano oxygen for some, but I never seen in the industrial process anybody use for CO2. But at this
Technically, it
pump,
should be
yes,
possible. Yeah.
we don't have corrosive gas and
Can you buy device the Alibaba? You say commercial one.
the pump.
The Alibaba.
Maybe we have it for
Yeah.
ozone, yes, the small one. But the bigger one, I can say, China, Japan, Netherlands, United States, many countries, they have the nanobubble pump. This is not a big
Okay.
thing.
Okay.
It's not a. I don't
Even
think it's a
small scale.
sophisticated, very small scale. Let's say
Yeah.
even 12 liter per hours is available.
So the demise of high flux and what Olivia transitioned over to was high oxygen content water, which is what she now does, and that's done with nanobubble. That's what it is.
Okay. Thank you, Lucas.
Please.
I like the idea, of converting CO2 into something chemically useful rather than sort of fake projects like using it for enhanced oil recovery, which simply brings up more CO2.
Yes, sir.
And which accounts for 90% of the carbon sequestration projects in the U.S. today. So it's really a bit of a boondoggle the way it's being practiced. I was curious about these two reactions in the bottom. They both seem to acidify. You have hydrochloric acid as a byproduct, right?
The point is, yes, you are right. But based on the KSP, don't even initially we have a reaction of the CO2 with the water producing bicarbonate. Bicarbonate is very strong ligand or chelating agent. Therefore, it's very fast separated, precipitate out. What we found, because of the diffusion of the CO2, we are able to control the crystal size and crystal form of the calcite. For example, now we have calcium carbonate, but not in the form of calcite. We have it in the form of aragonite. Aragonite is not soluble in HCl anymore. It's like some sea creature that they have shell, but those shell, they are not soluble in acid. That's a lesson that we took from the nature. We carefully check the crystal form of those animals. We found that instead of calcite, they have aragonite. If we control the diffusion of the CO2, we can control the size and form of the crystal. This form is not soluble in HCl anymore. Even we have a calcium carbonate.
Just looking at the reaction.
Yes, the reaction, if we want to just again eventually make it very economical, after the precipitation we can add again some ammonia and producing ammonium chloride and sell it as ammonia. That's it.
Yeah, I guess it would be interesting to see the complete sequence of envisioned reactions then, because I'm not fully following them here. You've got some intermediate steps that are not shown.
Yes, sir. I can say we have to be very clear, we have a bicarbonate, producing calcium carbonate plus HCl, but HCl is not able to dissolve the calcium carbonate. Accumulate, we can grab it if we want, we can grab it in the form of ammonium chloride.
So the question is,
Ocean acidification is dissolving the shells of sea creatures. And one other question on the nanobubbles. The rates of diffusion scale is 1 over the bubble diameter. So do you have to worry about things contained in the nanobubbles diffusing away from them?
We did not see anything. The reaction is almost instantaneous. As long as we have it.
So the gas inside the bubble is in full equilibrium with the bulk water around it?
Yes.
Okay.
But I can say maybe the best, at least at this stage, I have this. We have like a nano reactor. One, let's say, bubble based on
Yeah.
the surface. We have inside we have CO2, and we have on the boundary equilibrium between CO2 and water that forming bicarbonate. In the proximity, we have a significant amount of calcium. In the very nano size, we have a calcium carbonate. Therefore, we can this diffuse.
It's essentially encapsulated. Then.
Exactly. That's the reason that we have a different crystal structure. It's not amorphous. It's not like a calcium carbonate that very fast dissolving even the weak acid. We have some form of the calcium carbonate which is not soluble in acid anymore. Even this in the very strong acid, after 2 months, still we have it almost intact solid. Calcium carbonate inside the acid after 2 months. No bubble, no reaction.
So, if you're making veterite rather than calcite, is there a difference in the market value for this?
What market? Oh, for the veterite, I don't know. For aragonite, I think there's a big market. Big
So
market.
you're making veterite or aragonite?
Aragonite.
Oh, so you're making, sorry, that's what I'm asking. Is there a big difference in market value for your veterite rather than your calcite?
The point is, we have a significant amount of the natural calcite, but
Okay.
we don't have that much aragonite or veterite.
Sure.
If we are able to somehow, again, this is another thing that maybe NEOM can investigate. You have a calcium, or even the system that you discharge calcium and magnesium. If we are able to use just CO2, we are very close to zero discharge. But the new calcium carbonate, we can, with some modification, using as a calcite for the countertop. Some for commodity product, we can make some sort of rock that is very useful. But now we feel like we have an amorphous powder of the calcium carbonate. But when we have a nano CO2, we are able to control the rate of the reaction and grow in the crystal. Now we can have a very useful, like a natural compounds. But aragonite has the different market. That's, I think.
Yeah. Okay. But that's, the NEOM guys, you have to deal with about 5,500 tons of calcium sulfate a day, right?
But they don't have to make a sulfate. They can make calcium carbonate.
No, but what I'm saying is they have a lot of calcium.
Perfect.
Huge amount of calcium to deal with. So,
I guess we'll continue the discussion in a bit more. Thank you very much. And now we have Professor Shane from Qatar University as our last speaker before we go ahead with our guests. I'll introduce.
Yes,
We have,
just want to introduce our acting dean of the Faculty of Engineering IT, so Michael Blumenstein. And then our head of school in Civil and Environmental Engineering, so he's Dai Chao Shen. So they want to have lunch together and then share a little bit of discussion. So after last speaker from Shane, and then we will have lunch and then we can discuss together.
If you are hungry, I can.
to do calcium carbonate and get all of the.
So I want to focus on the electrochemical method. So my research, related to using the environmental electrochemical process. Mostly my work is related to the energy production directly splitting from water or using the CO2. And other is resource recovery. For example, lithium recovery from brine water. And another topic for my research is related to purify the water using the electrochemical method. Also, I'm now developing one electrochemical filter for the oil water separation from produced water. here I intensively focusing on the lithium recovery. Let's say we have a brine or direct seawater, so we use some low-grade heat. I don't mention in detail here now. So we have got the project from QNRF, Qatar National Research Foundation. We apply the CSP technology with thermoelectric system. So let's say out of brine can be used to cooling water. This is CSP-based thermoelectric device gonna be go to the some membrane distillation, and with electrochemical method to capture the lithium recovery from the concentrate the brine solution. But here we collaborate with Dr. Yuan Chen, University of Sydney, close here, and UTS Professor Shaw, very close to me. And we developed this design, and so here we combine all together the membrane distillation principle with lithium, the battery principle. So when we get some heated water, the while charging, the discharging, charging means discharging means we apply the potential, getting the lithium into the interconnect lithium manganese oxide. So and then at certain time we give us some charge time to capturing the lithium from solution. So this was actually in a small scale laboratory device. Here.
Yeah, unfortunately, it absorbs the background, so it doesn't work as a pointer.
So we applied the lithium selective electrode LMO, and so we can get some the heated water. And the heated water can be driving force in the MD system. The water going move to the colder side, and later we can get only lithium-ion solution by a Linz solution. So when you compare this extraction process with the others, conventional electrochemical method or other adsorption method, in terms of purity, when we increase the sodium lithium ratio, so our method reach good compared to the others, but it is similar to the conventional electrochemical method in higher the ratio value. Current depth is good, so when you have a higher ratio range, and also recovery rate is very important. So to compete with the conventional evaporation method like in Chile, so here, so our method showing a good summer assisted electrochemical method. Another one, so generally the CO2 conversion using the two compartment, the electrochemical system, but here we applied the one desalination chamber to utilize the saline water, the ions dissolve in saline hour. So like electrodialysis, we applied the selective anion cation exchange membrane. So in the ion in the saline water selectively moved by the exchange membrane toward a positively charged electrode by electrochemical attraction reaction. So in the cathode we put the CO2, and this sodium will increase the conductivity, and then the conversion rate is very fast. So finally we can get selective the bromate, getting a high Faraday efficiency by the our developed cathode material. We use the bismuth cathode. It's a very well known the production of a selective the bromate by the CO2 conversion, and also we developed some anode, to compress the water splitting to get selective the reactive chlorine species. They kind be some oxidant like sodium hypochlorite in desalination plant. Yeah. So we test urine as a model of the organic substance, and we get successfully good result. So here is CO2 conversion, and desalination process and water oxidation to purify the wastewater. Anyway, here all ion in saline water can be maximally utilized some target CO2 conversion. Yeah. Here, when you increase somehow to save the energy consumption to be used here, so we used some desalination stack. We can decrease the energy consumption by a factor of 5, and fully utilizing all of the ions in saline water, so we can get more to improve the CO2 conversion rate with many formate the production yield as well. So formate is one of the chemical material is kind of ammonia. So this is a hydrogen energy carrier. There is potential. So CO2 to make it utilize the carbon utilization, CO2 can be moved to formate to make hydrogen energy carrier. It has good potential to be used or saline water utilization. Another way is similar to systematic. So we doesn't put any CO2. So we also apply the selective electrode, compressed reactive chloride species to boost only water splitting, so that we can get water reduction to get hydrogen here. So here after reaction, this pH cathode area increased, but if we put CO2 by combined some CO2 electrolyzer, we can maximally also utilize the somehow mineralization. Our Texas A&M faculty show example, yeah. So we can somehow utilize the high pH with CO2 gas to make some mineralization. So another way, also John Reinhardt showed some example from here. So if we apply the bipolar membrane, so we selectively collect the acid and the production or base selectively, while keeping the same production of hydrogen and water splitting here. So also to save at energy consumption in boosting the production, you can also apply the desalination stack. That's all for my presentation. So.
The technologies you pointed out, at this point they're basically at scale level, I can see bench size facilities. How scalable would that be because of the complexity of what is being done?
Yes.
And are you using, for what kind of membranes you would be using for the process, for the, can that be scalable?
Similar,
Yeah.
almost, we use the piece film companies, the anion catalyst change membrane. They want to be used for scale up the electrodialysis. They're already scale up. The same stack, configuration, but approach is only different. Regarding the studying only CO2 conversion and hydrogen production using the desalination chamber stack.
Okay.
That then be possible to up like a TRS 7 or 8.
Okay. Yeah. Sounds good.
Thank you, Shane. So give a big hand. So due to our, catering for lunch, also our associate and the head of school timing. So first, let them have a little bit of talk for this meeting, and then we can have a lunch, and then we can have a discussion during the lunch time.
Sure.
So first, Michael, so can you give us a little bit of a short speech?
Well, I wasn't prepared to give a speech,
Yeah.
but I'd just like to say on behalf of the faculty, it's wonderful to have so many visitors coming to discuss this important issue and research area with UTS colleagues, and of course some or all of you already collaborating much with our UTS colleagues in this area. Sean and other members of the team have done a great job in growing this area in terms of attracting funding, publishing high quality work, and our faculty strategy is very much focused on growing the work that goes on in the the school and Sean's Associated Centre and the colleagues around the table. I just wanted to say also that our faculty, apart from having a strategy around investment in specific areas of research like technology in water and wastewater and areas relating to, well, we're a technology university, so anything relating to technology is important for us. But I also wanted to mention that our faculty strategy recently was announced in the first quarter of this year, and there were 3 areas that were overarching themes of where we'd like to focus on. So apart from the investment in individual centres and research, one of the areas is more broadly in the space of climate change sustainability. Now, I know that sounds not surprising. Everyone is focusing on that around the world, but I think what our faculty can bring to that area is that specific strength in engineering and technology that can really accelerate that space. I think the answer is obviously cooperation, collaboration internationally, but the effective use of engineering technology more broadly to advance those goals. So, in other words, what I'm saying is workshops such as this and the work that you're all doing in collaboration is very much a priority for our faculty, and we very much welcome your discussions, and I hope you have had and will have a fruitful technical session. So thank you.
Thank you.
Our head of school.
No, Sean, you asked me here for lunch.
Oh, there is no free lunch, I guess.
I just attended a conference in May in Darling Harbour. I hate big conferences. I mean, it's the best of times you walk around with a coffee and in the poster area catch up with someone from overseas. But such a venue with a small group of people who give a talk, we know each other. So that's the best communication style. I think Michael has said enough. UTS is a special university in Australia. It stands out in one aspect, our partnership with industry, our partnership with international institutes. I see the list that we have people from Saudi Arabia, we have people from MIT. So we really stand out, UTS. Every time the government does almost senior assessment evaluation, UTS stand out with impact, partnership. That's our nature. We don't have an MIT in Australia, but UTS is the closest to MIT in Australia. So thank you for coming here. Let's go have lunch.
Thank you for coming, both of you. Really appreciate. And then, okay, just to briefly, I want to say just your affiliation and the name, and then we will go for lunch together.
So I'm Christopher. I work with ETRI for SWIC, so with the research arm of the Sail and Water Conversion Corporation in Saudi Arabia. I'm one of the researchers, and I also a link between the labs and the researchers as well. So I come to the research in the labs and make it happen.
And you're Australian as well.
Yes.
My name is Hamid. I'm from the Texas A&M University.
I'm John Leonhardt. I direct the Adult Deep Water and Food Systems Lab at MIT, and I'm a professor of water and mechanical engineering.
It's Christopher's from NEOM, and I hope to use all these wonderful ideas that you are coming up with in industry to put them in practice.
I'm Rasta speaker.
Last speaker before lunch.
Yes.
Yeah, Nikolai Vuchkov. I also work with DTRI on leading the desalination brine mining program. So, and otherwise I am representative of the U.S. and do work with a number of different research institutions in the U.S. as through a small consulting company I have in the U.S.
Robert Garner from NEOM, as Anthony said, a very large scale practical implementation of all of this technology to achieve circularity in terms of desalination and recovery of materials?
My name is Hans Schouwvelder. I'm director of the Water Desalination BU Center at KAUST. That's a university in Saudi Arabia.
My name is Jay Chandler. I am an assistant professor in the Mechanical Engineering Department at Indian Institute of Technology, Gandhinagar.
Nice to meet you face to face.
Lunch is ready, right?
Yeah, ready.
So now is lunch is ready, so you can bring your lunch and then we can have a discussion together. Please, have a lunch.
Are we eating it here?
Photo, group photo together, yes.
This is going to be
What are social media?
yes. We need very important.
I like to play with the biofountains. These microbubbles, I like to put in microbubbles.
Yeah, bubbles are an interesting concept. It adds some features that are various different engineering uses, but it sounds very good. Yeah.
So there's some very contradictory statements on this.
But I think at a nano level, there are processes that like this, changing the structure of what you use for outside that is very interesting because they may features that we otherwise can use and that we don't get from the micro level.
Take a photo together.
Shall we come over here for a photo?
That really helps us to have a very easy. I mean, that's why I asked about energy because also, you know, I don't know exactly how much we're bound to do is to create non-bubbles when you.
If my memory recalls right, they were first discovered in practical
Yeah, I mean, I think so.
I think they can still produce them free.
Nobody was trying to do it right.
That's the other
Sugars will be there.